Okay, let's start our lecture number 7. I think it's going to be a little long lecture today. It has been like this in the previous lectures. I hope in the near upcoming lectures we have some shorter lectures so we can balance, the total amount of lecture hours in this course. This is the plan for today, our summary. We're going to talk about electrostatic, electrostatic energy, then we're going to conceptualize that now in material media, right? I mean, a general relationship between energy and sources and fields. Then we are going to describe how to solve electrostatic problems using either Laplace's or Poisson's equations. Laplace's equation being a particular case of Poisson's equations. We are going to do some, examples with high symmetry, configuration that have a high degree of symmetry, which we can solve the differential equations in closed form. We're going to talk about the formal solution of Poisson's equation, the integral solution. Talk about green functions and the uniqueness theorem, uniqueness of solution. Then we are going to conclude on the two important topics, which are in fact applications of boundary value problems in general. But I would like to include those applications in this lecture. And I will leave the other lectures for more complicated problems. We're going to talk about the concept of capacitance of a set of electrodes. And finally, we're going to describe a general principle called the principle of virtual work that allows us to determine the force between different bodies, the type of fields involved independent of if it is electrostatic or electric or magnetostatic, magnetic fields, or even gravitational fields, or other types of fields. It's a general principle that we can use to determine force. For instance, if you want to determine the force that a magnetized bar or a magnet have suppose you have a magnet and another magnetized bar, what's the force that this magnet pushes away or pulls this bar? I mean, you can determine those things using this principle. Okay. Well, let's start with the first topic. Well, the references for this lecture are those here. The ebook on chapter 2, Jackson chapter 2, and African chapters 2, 9, and 10. It talks about Green's functions, the formal solution of Poisson's equations. Suppose that you have built a system, you have assembled a system in which you have the coexistence of, space charges, free charges, right? And like this one, I mean, those funny forms, this one here looks like a dish or something like that. And some dielectrics, right? Those here, shown here. Sorry for the delay here. My device is a little slow today. I don't know why. I mean, all these elements occupy a volume V, And we want to determine what would be the electrostatic energy change for an incremental change of charge density. You see that, let's state that at a given state, the potential function in the system is described by this parameter phi. Okay, so if I increase the charge everywhere, right? In a volume element, dV, if I increase the charge density by delta V, we are going to have a charge variation only on dV that's given by this change. So the energy, in principle, if I have already established potential, the changing energy is the change due to the addition of this incremental charge. So we change the density by delta whole, and the charge change in the volume is delta rho dV, and the entire change of energy is given by this expression. So we can build then the expression for the energy going with the density changing continuously from a starting value, let's say 0, to a final value, rho f. Accordingly, the potential function, sorry, let me just do something here. The potential function, just a second, just scan my class notes here so I can see them. Let's just do this thing here. Okay. So the potential function will change, right, to a final value rho f. So the final energy is going to be that due to a change, the final electrical energy, let's say, is going to be that corresponding to this total change of charge density from 0 to rho f in some nonlinear media. Nonlinear because of the polarization, might be nonlinear. The response of polarization to the application of an E field might be a nonlinear function, as we saw, as we briefly described before, previously. We have hysteresis, which is one of the features of nonlinearities in those systems. So, in a nonlinear medium, for instance, we can look at the plot of how potential changes with rho, right? Then you might have this nonlinear function here. That would happen if you have a dielectric nearby the free charges that makes the induced polarization charges respond nonlinearly to the applied field. If we had just vacuum, that wouldn't happen. You have a charge, unless you have very intense fields so that you break, you ionize the charges or the system of charges so that the system can reach a nonlinear state. But normally, if you have vacuum and free charges, the system is linear, right? For a vacuum, you have something like this, right? Relation between potential and charge density. So you can distinguish those two situations by looking at how the potential responds to the variation of rho. If you have a linear system, have this type of thing, right? So we can calculate the energy at the final state by introducing variable k that is a scale factor times, the density is a scale factor k times rho f. If the system is linear, right, then accordingly the potential function at any state will be the same scale factor times the final value, right? So this linearity implies that the ratio between potential and charge density at any stage, at any state, during which the rho changes continuously from 0 to the final value, is always constant, which is the final value of the potential function divided by the final value of the density. So if you look at the integral that we have, let me just close this one. We have this integral here, right? So let's look at this. Let me copy that to here, and let's look what happens to this integral. This is just the change at a given state of rho. So the final energy is equals to integration from 0. Let's make like this, rho f, then volume integral of phi delta rho dv, but this dv is the volume, this is correct, dv. I'm going to interchange the integral. It's going to be written like this, volume integral dv. Then I have another integral here, which is this one here, right? 0 to rho f of phi delta rho. Now, if the system is linear, it means that rho equals to k times the final value, and delta rho is delta k times the final value. So I make a change in variables, and recalling that phi by itself is the same scale factor times the final value, and those are constant relative to the integration here. So the integral can be written like this, integral from 0 to 1. Now I change the variables, right? Then you have phi, which is this thing here, k phi f. Delta rho is this thing here, delta k rho f. This is not a k here. Sorry about that. Rho f. Then, these things can be placed outside of integral symbol because they are constant. They are not variables here. Integral from 0 to 1 of k dk, k delta k, k delta k. And this is k squared over 2 from 0 to 1. So the integral in the state space, which is this one space in which we change the charge density, is going to be 1/2. This is 1/2, right? Of the rho f phi f. So when we have a linear system, if I plug this back here, we have this thing here. The final energy, let's say WE, let's now go back to the symbol, traditional symbol. This is phi at the final state. Rho f, let's call it rho at the final state. So when you do it, it's going to be 1/2 volume integral of dv rho times phi. That's the result we got previously, right? That's what we have previously. This is the result. So this is the final state, has a rho or rho f. I just dropped the subscript. Final state has a final potential distribution phi f or phi. Then the energy is 1/2 of those this product integrated on the volume. Otherwise, if the system is not linear, the way you have to calculate the energy during this integration first in the state space. State space is a state in which we don't have a coordinate, but just, the state dependence In each point, the system has a given state, represented by the value of potential and value of charge density. So we have to determine this curve to make the integration in the state space, which is this one here. Then after that is completed, we do the volume integral and calculate the energy. So in general, that's how you calculate energy for any system. It can be a linear or non-linear system, okay? Right here. Very well. What happens in the... I mean, we had expressions for energy in the source point of view and in the field point of view, in the field framework. What happens in the field framework? Well, in the field framework, we have to see how Maxwell's equations change for incremental change of the rho of the charge density. So if there's an incremental change delta rho in the charge density, there will be a corresponding change delta d in the flux density vector, in the displacement vector. And these things are related by one of Maxwell's equations. The divergence of this change in d is equals to the change, incremental change in charge density. And now, if we replace delta rho in our expression by divergence of delta d, right? Then we have, that's the same expression, it's phi. Delta rho is right here, right? Now, if we do the same procedure that we did before for a linear system, you know, I just use the fact that there's some things that we did before, right? We use basically the fact that divergence of a function times a vector, right? Our vector is delta d in this case, equals function divergence of delta d. That's the term that is in the integral, minus delta d dot gradient of the function. So we have this term here, so it becomes phi divergent of delta d, which is the original integral, equals to, then you have one term is this one, and this one, in fact, is, sorry, this is plus, right? This is not right. So in this term, when I isolate this one, it's going to be minus delta d dot gradient plus divergence of the whole thing. And this is nothing more than minus delta d, I mean delta d dot e. E is minus gradient of phi. So I have this term here, right, which appears. And we have this volume integral of this vector. The volume integral, we use divergence theorem, as we did before already. I'm going to let you do this to complete this demonstration. And it can be shown that the integral of this, I mean, this, by Gauss's theorem, this becomes a surface integral of this, of the flux of this vector. And the flux of this vector, recall that, I mean, traditionally, the potential far away from distribution is 1 over r, and the flux density is 1 over r square, and area goes with square of r. So we make a limit, r squared divided by r cubed is 1 over r, in the limit as r is very large, so you can include all the dielectrics and charge densities in your system, then you have a zero result. So this term is not going to contribute, and you're going to be left with this term here, right? So that's why you get a final expression in the framework of the field. So the final energy is given by this. First, we have to make an integration, a fun integral, right? I mean, the upper limit is a vector. I mean, it's the state of the final vector D. What's the final state, right? And this is a line integral in the space state. Yeah, it's a Hilbert space, a generalized Hilbert space. It means that the coordinates are not, geometric coordinates, but abstract components of a vector. I mean, it can be anything, but in this case, we have some meaning. Is a space state is a space in which, in this case, right, we are doing integration. The integration variable is d. So we are going from an initial state, let's say d equals 0, to a final state, d equals df, through a path. Now, that's d. We have to determine how d and e are related. We are integrating e as a function of d, right? Delta d. So that's the delta d is a displacement vector like here. So that's an integration over a path in the space state, right? That's how we have to do this integral. We have to integrate from the initial state to the final state in this space state to determine the energy in general for any nonlinear system, okay? There's a general expression for energy in an electrostatic system, whatever the system is, if it's linear or nonlinear. Okay. If the system is linear, then things become much easier, right? Again, I mean, you can parameterize the vector d at any point. You can change it as a multiple of a given value for an isotropic system, right? Also. So the ratio between E and D in a linear system, right, is constant, is the permittivity of the medium, equals to the final values, the ratio between final values. So we can, again, parameterize by a variable k, as we did for the potential. And we are going to essentially have the integral of this integral here, right? Integral of k dk is going to be k dk from 0 to 1 is going to be half. So we're going to have a factor of 1/2 coming in. And the energy becomes that energy that we derived earlier, I mean previously. Okay? This is also valid for any anisotropic medium, not only isotropic. I'm going to leave it for you to try to discover how to demonstrate that. It's not difficult. You can use the same principles. Even if the system is anisotropic, it's going to have that expression. I mean, linearly anisotropic is going to have that final expression for energy. Okay, so we have now energy in whatever the system is, okay? Well, let's now see how is the formalism for solving problems in electrostatics. Problems always end in a second order differential equation that can be solved, right? Let's assume also that the system is linear. If the system is non-linear, then the differential equation that we are going to have is non-linear and very hard to solve. I mean, it depends on each case, on each different type of media of different types of non-linearity. You can have a different solution, different type of solution. Now we're going to look at the case of linear systems in which we have a broad class of problems and practical situations. So if we have a linear system, how are the Maxwell's equations, right? Well, for a linear system, we have first that D and E are related by the permittivity of the medium. And if we plug that into one of the Maxwell's equations, that the Gauss's law in differential form, differential form of Gauss's law, right? This is divergence of the equals the free charge density. Recall, this parameter here is the free charge density. That's one equation. The second equation is the one that gives the curl of E, which is always 0 in electrostatics. Because of this, E can always be written as the gradient of a scalar function. We put a negative sign here because that came up naturally before, right? So when you do that, if this is the type of potential function we define, it's going to be directly related to the energy of a point charge in a field. So that's why this negative sign has some importance. But we could use another potential function with a positive sign, for instance. Okay. Now, when we plug this E into here, then we have a second, we have still a complicated equation, not simple. Divergence of epsilon gradient of phi equals to minus rho. Now is the key consideration here. If we have an homogeneous medium, right, means that the epsilon function is not dependent on the coordinates in the medium. Epsilon is constant, homogeneous mediums, the same properties everywhere. Okay. Then we have and also isotropic, because if it's anisotropic, it would be more complicated to expand this equation. So let's say that's also isotropic medium and not homogeneous medium. So this depends on coordinates and direction space. So otherwise we'd have a more complicated relationship. Then if you do that, the epsilon goes out of the derivative here, right? And we have the divergence of the gradient of the potential, which is the Laplacian of phi equals to minus rho over epsilon. It's important, this is a non-homogeneous equation. This is called the Poisson's equation. Okay. Now, if you have the special case, sometimes you have to break the problem in regions. Some regions have charge distribution, other regions don't. Or sometimes we have point charges in most parts of the volume, charge is 0, only in certain discrete points. So in many cases, you can solve the problem when you have surface charge densities on electrodes, on conductors also. They are not volume charged, they are just charged that are localized on surfaces or charged lines. Then you have volume density equals 0, unless you can represent that by a delta function, right? But in most part of the volume, rho equals 0, then you have Laplacian of phi. Maybe I should say Laplacian because of Laplace. His name is Laplace, right? So Laplacian is better instead of Laplacian. Instead of flexing the letter A. Laplacian of phi equals 0. So this is called the Laplace's equation. Laplacian of phi equals 0. And of course, the non-homogeneous equation, which is Poisson's equation, the solution can be broken in two parts. A homogeneous part, which is the solution of this problem here, and a particular solution that depends on the charge density. Okay? So every time you solve Poisson's equation, part of the solution would be the solution of the homogeneous equation, which is Laplace's equation. So we're going to do some examples on how to solve either Poisson's or Laplace's equation for certain problems that have high symmetry. So it means that we know a priori that potential depends only on one variable, and we are going to choose the coordinate system more suitable to solve the problem. Let's start with a very simple problem. We already derived the potential of a point charge, by the integral solution using delta function. Now we are going to solve a differential equation related to the point charge placed at x equals 0, okay? So we have that situation depicted in this picture here. So we have a charge Q embedded in a homogeneous medium of permittivity epsilon, let's say. And the system has symmetry in which the quantities here depends only on distance. The potential depends only on the distance, doesn't depend on angles, right? So we know a priori that phi depends only on the radial coordinates. We can write for the charge density this relationship, charge density equals to Q delta of x picks up at x equals 0. So Poisson's equation is this one here, right? But for x different from 0, so we have a Laplace equation. So let's look at the solution for x different than 0, knowing that phi is only a function of the radial coordinates. So for x different than 0, for x different than 0, we have Laplacian's equation. And because of that, the potential depends only on r, right? So we have this form, the radial part of the Laplacian. If we solve this equation, let me do it quickly here. 1 over r squared, we're going to use that later, so we're going to solve it here quickly. So we have this differential equation here, which is the Laplacian in spherical coordinates, only the radial part. So equals 0, so we multiply by r squared. We have ddr, r squared, the phi dr, equals 0. We make a first integration. Recall that every time you make an integration, you have arbitrary constants that you have to introduce in the problem, because those constants have to find out what they are later. So first integration gives a constant. I'm going to choose a negative sign in front of the constant. You understand why in a second. Then you have the phi dr equals to minus a over r. Because I don't know what the value of the constant, I can put any sign I want. No problem, right? So the phi dr is minus a over divided by r squared. So integrating again, the integral of a minus 1 over r squared is 1 over r. So it's going to be a over r plus b and other constants, right? That's the general solution of Laplacian's equation in spherical coordinates for potential depends only on the radial distance. So we solved that. Then we have that, I did exchange the constants here, a plus b over r, right? Same thing, but the general form is a constant plus the inverse function times a constant. So when you solve those equations, you have to have some physical considerations to obtain the two constants, right? Well, we have two information here, two pieces of information. First one, we have a charge in the origin, And second one, the effect dies out to 0, let's say, for r very large. So to obtain A and B, we are going to use those two considerations. When the distance is very large, let's assume that the potential goes to 0. Otherwise, it's going to be a constant value that is irrelevant for determining the field. Recall that every time you solve for the potential, the final thing you want to determine is the field. So any arbitrary constant is going to vanish when you calculate the gradient of the function. So if you use that property, first property, I mean, this thing goes away, this goes to 0. So the only remaining part is this constant here. It has to be set to 0, so that the potential goes to 0 at infinity. So the potential now has only one constant to be determined, and what is the value of this constant? Now we have to turn back our attention to the Poisson's equation and the charge density that is concentrated at x equals 0. Okay? So we have to look at that information. So that's the equation we have. We are going to integrate around the origin so we can have a finite value for the integral of the delta function. So we can pick the charge, right? So we have that volume integral equals to minus q over epsilon integral of the delta function around the origin. It means that we are integrating a small sphere of radius r0 around the origin. This is going to be simply equals to 1, right? And you have the result is minus q over epsilon. And now we go here. Look at this integral, left-hand side. Integral of the Laplacian of phi, which is the divergence of the gradient of phi on a volume, which is by Gauss's law is equals to the flux of this vector across the surface outwards, right? And it's not, I mean, let's just do here, right? Potential is B over R. The gradient equals to minus B over R squared AR. So, and the sigma, I mean, over the surface of radius R0, this is going to be R0 squared. And the sigma is going to be R0 squared d omega AR. So it's not difficult to calculate the integral because we are going to cut R0 squared. So you're going to have a constant, an integral of the solid angle over the closed surface, which is 4 pi. So the integral is minus 4 pi b. So when you compare this with minus q over epsilon, you have the constant b, which is the second unknown. One is a, which was 0 for the boundary condition at infinity. The other one is in the origin. So we have the final response, right? I mean, you see that we formally solved differential equation. Every time we have delta functions, we have to integrate around the singularity to pick up the results of that density function represented by the delta function. Well, one important result of this problem is one result that we are going to employ when we derive the Green's function for the Poisson's equation. So, the Laplacian for the inverse function. What is the Laplace of the inverse function, right? Well, just look at the result that we got, right? I mean, if we have a Laplacian of the q over 4 pi epsilon r, there's a Poisson's equation for the charge density equals to Q delta. So if we equate those two quantities, we have the final results, right? Notice that R equals to the magnitude of the position vector. So we're going to have this result, Laplacian of 1 over magnitude of x equals to minus 4 pi delta of x. If we shift the origin to x prime, right, we're going to have this other result, Laplacian of the inverse function represented by the inverse of the magnitude of x minus x prime equals to minus 4 pi delta of x minus x prime. Okay. We can interchange the quantities here. Let's say here, suppose that I have how much is Laplacian of one, let's say that's relative to the prime variable, right? So derivatives are for the prime variable. So 1 over x prime minus x, same result, equals to minus 4 pi delta of x prime minus x. Okay. So notice that delta function is always an even function. This is also delta of x minus x prime. So, I mean, we can use whatever form of the Laplacian of the inverse function. Okay, it's not difficult to do it. But we have now to always use this result. We're going to employ this for Green's function definitions. We're going to use that property. Let's do some additional examples of solving Laplace's equation. I'm going to just outline the solutions, and I ask you to work out those solutions, okay? Let's say this problem here, in which you have a region inside a sphere of radius a, which has a uniform charge distribution of rho 0. The sphere has a radius a, and inside of the sphere you have those, you have those dust, charged dust. So you pulverize the region with charged dust. You have a vacuum and charge distributed. Or you can imagine a paste, a volume paste, right? Which you fill up this sphere with this material that's charged, but you have vacuum and charge. And outside you have a dielectric medium that covers the whole space outside. Let's say that this sphere is inside water, right? So you have a dielectric is the water in a pool. You have a small conducting sphere which is charges drop in the pool. You want to know what's the potential distribution inside and outside of the sphere. So now we have to break the problem in two problems, right? Because we have different regions, have different regions. Let's call region 1. I think this is wrong here. I have a small, I hope this error doesn't propagate. In the region 1, which is this one, permittivity is epsilon 0. So here we have the Poisson's equation with the permittivity epsilon 0 inside. And outside have the rho equals 0 outside, right? So we have Laplace's equation. We know the general solution outside, which is for a spherical symmetrical problem, which is this one. Again, the potential only depends on the distance r. So we have already the solution outside, general, right? Two constants. Inside have to integrate. If you do the integration inside, now, I hope you do that calculation. One part is going to be the homogeneous solution inside. Notice that the constants are different constants, right? It's not the same as the constants here, because we are talking about different regions, right? Each one has its own constants. And you have this additional term here, which came from the non-homogeneous element that is on the right-hand side of Poisson's equation. So Poisson's equation solution has a particular solution, depends on the density, and a homogeneous solution, which is the same form as we derived in the previous example. So I have 4 constants to be determined, A1, B1, A2, B2. We need 4 conditions, 4 equations to solve those constants. So what are the physical considerations? Well, potential outside for large R is 0, right? Potential inside has no singularities because we are talking about a continuous distribution. There is no discrete charges inside here. So in the origin specifically, there is no singularity. You notice that the solution inside has one term that gives a singularity in the origin. So there's the second condition, which is no singularity in the origin, right? I'm going to look at the constants of those conditions. The other is the uniqueness of the potential solution. I mean, and in a boundary between 2 different regions, the potential calculated from one side has to be the same as that calculated from the other side. So we have unique value of the potential at R equals A. I'm going to look at that. And the other 4th condition has to do with the boundary conditions for the E field and for the displacement vector, right? E field means that tangential E is continuous. That is a direct consequence of the fact that potential is continuous. So that tangential E being continuous doesn't give any additional information. So one condition is this one, n cross the difference vector equals 0. So tangential E, I'm going to put it like this because there are three equations here. The other one is n dot d2 minus d1 is the surface charge density if there is any present in the problem. Notice that in this example, we don't have any surface charges. Charge is only a volumetric type charge. There's no charge on the surface, localized on the surface. Okay, that's known a priori. So the boundary condition that involves D now is there's the 4th independent condition, is the normal D is continuous at the boundary. Okay. So that gives a condition involving the normal D, just put here. Normal D means the radial D, okay, which is equal to, depending on the medium, epsilon I, EI, let's call like this, ERI, and in turn, ERI equals to minus gradient along the radial direction, which is minus d phi I dr. So in fact, I mean, dri can be directly related to the derivative and the epsilon of medium I. I'll have a sign here, minus d phi I dr. So continuity of the normal component of D means that inside epsilon 0 d phi 1 dr, where, well, at r equals a, equals to epsilon, which is the outside permittivity. The potential on the outside is phi 2 dr at r equals a. So we have that. So that's the fourth equation. So I have four equations at four unknowns. So this is a linear system of equations, easy to solve. Okay, so I have that condition here. I just demonstrated to you. So I left for you to solve those conditions. Just going to outline those. The constant for the solution outside has to be 0 for the potential to go to 0, as we did in the previous example. Singularity inside is eliminated by removing the term that contains the singularity, which is this one, just setting B1 equals 0. So we solved two equations, A2 and B1, so we're left with two constants to be solved. So we have this solution. I will leave it for you. I mean, you can go through the notes to see how to solve it. So we have the solution outside, which is the inverse dependence of the potential, as if we had a point charge at the center. And inside we have something that is quadratic, with a minus sign in front of a quadratic term here, right? And the solution depends on the relative size of the permittivities. If the permittivities are the same, I mean, you can calculate the field too, right? So we have the field. You can calculate the field inside and outside. So that's the method. You find the potential function, which is the intermediate auxiliary function. Then you go to the final quantity you want to determine, which is the potential. So that's the solution. Inside is a linear function. We already showed that before using Gauss's law and superposition, which is the integral solution directly to the field. Now we are showing a differential equation, another method, right? And outside, the field drops as 1 over r squared, as expected. If we look at the plot of those functions, I mean, if the permittivities are the same, you're going to see something like this for the potential and for the field. I mean, the potential has quadratic, the parabolic behavior inside, with a zero derivative at r equals 0. And if the permittivities are the same, have a continuous derivative, have a continuous derivative here. This is the 1 over r. This is minus r squared dependence. Okay. There are some other features you can extract from this. And the field, on the other hand, goes like this. Let me do that. This is the potential. This is for epsilon equals to epsilon 0. Otherwise, you don't have a continuous derivative. I mean, if epsilon, a continuous derivative is only for epsilon equals epsilon 0. Otherwise, we know that there's a discontinuity in derivative because of the boundary condition for D, which imposes that the normal derivative of phi is discontinuous. Okay. Now for the field, they have a increase linearly as we did before, then it goes 1 over r squared. Right? You can look at additional examples. I'm going to make another one with you. For instance, I will leave for exercise. I hope you do, because that will be, it's going to be asked of you if you know how to do those things later. I mean, in the exams and the homeworks. So do it. So we have, for instance, this problem, have just a surface charge density. Again, have two situations. Laplacian outside is 0. Laplacian inside is 0. The functions are continuous across the boundary. but we have a surface charge density that gives a discontinuity in the normal component of the electric displacement vector, or the electric flux density vector. Here, another example, we have two grounded, surfaces, two conductors. This is a shell, let's say, this one here. There's a shell, which is grounded, and we have an inner spherical electrode, which is also grounded, and we have an intermediate layer, an intermediate shell, spherical shell, which is charged with a given charge density. Then you have two regions again, right? I mean, outside is not important to solve the problem, but we want you to know what happens. For instance, you might want to know what is how charges, if you charge with amount of charging here, what is the charge distribution on these two electrodes, on this one and on this one, right? That's an important question. How much charge goes to each side? So we do that by solving for the potential in region 2 and region 1 and doing boundary conditions. Now notice that in this case we don't have the origin. I mean, for this region here you can have the inverse function because it doesn't have any singularity in this region here. So I will leave for you to solve it. I'll do this other one here, which is an example of a delta function in cylindrical coordinates. These are our examples of high symmetry, right? We are going to deal with problems with dependence of the potential with more than one variable. We have to use different methods, but now we can solve, by direct integration of the differential equation. So if we have now a line charge surrounded by a grounded cylindrical shell on electrodes, let's say this is infinitely long, which facilitates our analysis, because now we have only a dependence with we don't have dependence with the phi coordinate nor with the z coordinate. We have only a dependence of quantities with the distance r. We can represent the density by a delta function again, right? A linear constant density. We showed that before. The density can be written as a linear density times delta function of the radial variable, which guarantees the existence of something here at the z-axis, right? Divided by 2 pi r. So let's solve the problem. We have, let's say that the permittivity is that of vacuum. Again, I'll outline the solution here. So we have Laplacian of phi equals to minus rho over epsilon 0. The region that we are talking about is that region inside of the cylinder. Outside of the z-axis, we have the Laplace's equation. We have only dependence on r. Laplacian in cylindrical coordinates, when you have only the r dependence, is given by this expression. In spherical, we have a square here, right? And a square there. In cylindrical is just 1 over r, first derivative, and an r term inside. This is also easy to calculate if you solve it by two-step integrations. Make a first integration, multiply by r here, right? So we have ddr, just to show you quickly, of r d phi dr equals 0. You integrate once, you're going to have a constant, right? R d phi dr to make it equal to this one equals to b. So I'm going to have this goes as a denominator here, right? If we make another integration, we're going to have the logarithm of r. So we have a general solution given by this form here. That's the homogeneous solution. And we have to use one of the boundary conditions that the potential is grounded at r equals a. So we have one condition between a and b, right? I forgot to make a draft of this, and I'm writing on top of my notes, which I didn't want to do. I'll have to fix that later. Let me make a quick operation here so I don't screw up my 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 original notes here. Let me duplicate. I always forget one of those important steps, you know. So let me done. This one here is going to rephrase it. Rephrase it. Draft. So I can write on it. So probably have to fix my original notes that I have. Okay, so let's go back to this one here. Not that. Let's save that one. Okay, so where are we? Well, okay, we are here. So that's the general solution. We have one equation relating A and B. Okay, in this case we didn't have a constant equals 0. We have two constants. We have to use those. So I have this condition. Second condition is the information that we have a charge line on the z-axis. So we're going to integrate the original equation. Let me just write here. Laplacian of phi equal minus rho. Rho equals to lambda divided by 2 pi r delta of r. So what we're going to do is to integrate around the z-axis. Let's say is a volume r smaller or equal than r0. So we're going to do this thing here in this region. So we have the volume here. Let's put the dv there, right? So just recall this is r dr d phi dz. We are going to integrate on a finite region of the zx. So it's going to be on a region in which modulus of z is smaller than a certain value. Let's say in this example, L over 2. So also that's the region of integration. So if we apply Gauss's law here, this is going to be the flux, right? We have a cylinder like this of height equals to L and radius equals to R0. So Gauss's law gives us the flux of I mean, you don't have any flux on the top surface and the lower surface because the normal is orthogonal to the gradient of the potential. So we have that thing here. We have a gradient of phi in the surface r equals r0, and the surface goes from in this region here, right? Minus L over 2, and the surface element equals to so we have a length r d phi and a height dz. So the vector is this times ar, and the gradient equals to ar in cylindrical coordinates d phi dr. So this calculated at R0, right? So the surface is at R equals R0. If you look at the expression for the potential, d phi dr equals to B over R at R0 is B over R0. So this is going to be AR B over R0. So when you do the dot product, the sigma dot gradient of phi, so we cancel out this R0. So we have integral from minus L over 2 to L over 2 dz, integral from 0 to pi of d phi times b. I hope it's right. So it's going to be b times L times 2 pi. That's the result of one side of the equation, which is this result here, right? The other side is just the integral of a delta function in a region that includes the singularity, which is going to be 1. Then I have 2 pi here, and we have L here, 2 pi L. The 2 pi cancels, so we have lambda L over epsilon 0 with the minus sign. Then we have a way to find B. So that's what we got. We have B. And we have another relation between A and B. We just derived, right, the previous page. In this page here, there is one condition relating A and B, and I just determined B. So we have the result here for A, right? So that's the final result for the potential. Can be written like this. You can see by inspection, right? We have a singularity in the z-axis, r equals 0. The logarithm, natural logarithm of r of 0 is minus infinity. And at r equals a, we have a grounded potential. Potential goes to 0. And then you can calculate the final quantity, which is the E field. That's the result we got before. Now solving Poisson's equation. Okay, so these are some examples of high symmetry situations in which we have very well behaved surfaces, in which the dependence is only on one coordinate. Let's find the general solution of Poisson's equation. Initially, let's assume that, well, if we have a charge distribution inside an infinite medium that is homogeneous, we already know the solution of Poisson's equation. So I mean, if we look at this integral expression, this is the solution of Poisson's equation in an unbounded medium of permittivity epsilon for a charge distribution inside of this medium given by rho. Let's check that this is correct, okay? Let's make sure that this is right. We're saying that that's true because, I mean, the potential for charge density in an unbound region or in an unlimited region is, we show that it came out, we came with this expression here, right? At the same time, it showed that potential satisfies Poisson's equation. So we know that this is the solution, but let's show you now again to make sure that you believe us, okay? Let's calculate the Laplacian of that expression. So we just plug the expression. Recall that Laplacian acts on x in this expression here, right? And the integration is being done on the variable x prime. So dv prime is related to x prime. So I can interchange the symbols of integral and Laplacian, because Laplacian doesn't act on the integration variable. And I can just go to apply this directly to the inverse function, right? So I can just overpass, just pass the Laplacian directly. Then we are going to be left with this term that depends only on has only constants on x prime, and we are going to have Laplacian applied to the inverse function. We just showed you that the Laplacian of the inverse function equals to minus 4 pi delta of x minus x prime. So the 4 pi here cancels that. The minus sign goes outside. Epsilon goes outside of the expression. And then we end up with an integral that involves a function, rho, and the delta function that picks up at x prime. And of course, the integral gives rho of x at point x, which is the point where we are calculating the Laplacian of phi. So that's the result we got, so Poisson's equation. Indeed, the integral expression satisfies Laplace's equation. Okay. Now, notice that we didn't include any boundary surfaces that impose restrictions on the potential function. Now, how do we solve a problem in which we have, besides charge distributions in volumes, we can have, for instance, electrodes that impose certain boundary conditions, right, on the potential. For instance, if this blue thing here is a conductor, it means that the potential has to be 0 on the surface. I mean, it has to be constant, not 0, constant, right? So I have a restricted behavior on the boundary. So let's look at the elements that define this construction here. We have a charge distribution. I'm just enclosing that in a in a single region, but you could have pieces of that, other charge distributions in other places. Here, doesn't matter. We have a charge distribution represented by the function rho. Okay, the requirement is that the whole thing has at least piecewise. We have we can have a permittivity app. Let's start with a single permittivity. Then we can put different media together and can do the same procedure for each media. So let's assume that we have one single permittivity, one single homogeneous medium to formally solve the problem. So the general solution of the potential in this case, I mean, at least formally, can be determined using some theorems, or some integral theorems. I believe we did some of that in our mathematical review, but I'm going to demonstrate here. I'm not sure if I did the green identity, so let's do that. So the general solution can be obtained using Green's identities. Let's recall one important, Green's identities is a result of Gauss's theorem. Let's consider that our vector involved, the vector used in Gauss's theorem is written like this. Okay? I'm going to use two different scalar functions, psi and phi. because one of them is going to be the potential, the other one is going to satisfy one important condition we already derived. So Gauss's theorem establishes that the integral, the volume, I forgot here, the volume integral of divergence of A equals to the integral of the projection of A on the boundary, the normal component of A, on the boundary that involves the volume V. So we have the normal component and the surface element. This is the same as A dot the sigma, which is A dot n the sigma, which is A normal the sigma. Okay? So that's the same thing. So if you look at AN is simply, let me do it separately here. You have A equals to phi, is psi, gradient of phi, and A normal is A dot the normal coordinate. That's the boundary, okay? That's the normal coordinate that goes outwards. So this is psi n dot nabla applied to phi. Well, this is the normal component of the nabla, which is the derivative relative to the normal coordinate I'm going to call xn. Okay? So you see that x dot n, or let's say dx dot n equals to dx normal. So let's say that we have a normal coordinate. Every point on the surface that is represented by x normal, and the differential is dx normal. So, and the x normal is the length, differential length, because x is in the geometrical space, Euclidean space, right? So we have that derivative. So that's essentially equals to psi d phi dx n. That's what we have on the boundary. The normal component of A is given by the simple relationship here. So that's what we have. Gauss's theorem gives me the divergence of A in the volume equals to the surface integral of this combination of function times derivative of the other function. Now, let's expand divergent of A. It's the chain rule that we derived previously, right? It's one function times the divergent of the second vector of the vector, which is the Laplacian of the function, plus gradient of the first dot product with the second vector. So that's what we have. So if we, that's the Gauss's theorem. If we expand this in the chain rule above, this one here, we're going to end up, right, with one term which contains Laplacian of phi, and the other term that has gradient of phi, gradient of psi, right? And on the surface we have that term there, right? That gives me the Green's, this is incomplete here, sorry. Green, let me just fix this here. Green's first identity, right? Which is something like this. It's just a simple integral relation that relates operations in the volume, differential operations involving Nabla and Laplacian, and the normal derivative of one function on the surface times the other function. Now we can do the same thing. We can repeat this identity, changing phi with psi. I can do this like this. Phi Laplacian of psi plus, this is unchanged, right? Interchange phi and psi. And here we're going to have phi normal derivative of psi. So we have a second relation, and we can subtract this one from the other one. When we do that, we're going to have a cancellation of this term and a difference on the surface, and we're going to have a difference of terms like this, right? So you can work this out. Then we have the second green identity, right? So you can see that's very easy to see, right? I mean, we have a difference of Laplacians times the function, times the other function, and a difference of combinations like those. That's second Green's identity. So in summary, we have those two identities that can be used. I mean, you can choose any function I want to use those identities. I'm going to use the second identity, just recalling that xn is the projection of x along the normal direction, so it's derivative relative to the normal coordinates. Let's use the second identity, and for now I'm going to derive a possible integral expression for phi. Let's use these two functions. Let's say that phi is a function which is the potential function to the problem, to the original problem, has a Laplacian that's related to the charge density. The second function, I'm going to use a specific one, which is the function that gives, this is wrong here, a Laplacian of psi equals to minus 4 pi delta, right? Let's choose this option here, right? The function, I can use the inverse function because the Laplacian of inverse function is minus 4 pi delta. Recall that, notice that I change here the prime, right? Because I use the integration in the prime variable. Inside of the integration, we have the Laplacian on the primate variables. So let's use this function here as the second one, inverse function. Then what happens? Phi Laplacian of the inverse function is minus 4 pi delta, x prime minus x. Integration variable is x prime. So obviously this is going to be in the whole space. So the result is going to be minus 4 pi phi of x. Okay? The second term, what happens? The other term is Laplacian of phi equals to minus rho over epsilon, this is right here, times the other function. The other function is the inverse function, is right here. And we have the result on the surface. One term has the function times derivative of the inverse function relative to the normal. We have to find out what the normal is, right? And the other is the inverse function times derivative of the potential function on the surface. So what happens? Here the integral gives me directly the potential at any point inside of the volume. And now I can express finally the potential as a solution, a formal solution, an integral form, right? That contains that term that we had before, integration of the charge density, and the influence of the surface, okay, on the solution. I mean, that's the influence of the surface. If there's no surface, there's no bounding surface, this term doesn't exist, and we can simply remove it. Oh, sorry about that. I can remove a little less. It's simply just something like this. I can simply delete it. That's the solution. Otherwise, we have the complete solution. So what we see in the solution, that the potential depends on rho, right here, and on the boundary conditions. What are the boundary conditions? Well, information on phi and on the normal derivative of phi on the surface. Those problems have a general classification in math, the differential equations, and the, when dealing with differential equations, the theory of the differential equations. Well, if the potential, if the unknown function is specified, we call this problem the Dirichlet boundary value problem. We are going to use that acronym throughout this course, BVP, as boundary value problem. Right? Those are classified as boundary value problems, in which you solve a differential equation subject to the boundary conditions on the bounding surface of the volume. If we specify the derivative, on the other hand, we have a Neumann boundary value problem. Okay? And it's important to understand that each problem, I mean, these are independent. If I specify potential, I have one solution. If we specify potential, the normal derivative, I have a different solution. They are not the same. So these are independent problems, right? So those BVPs yield distinct solutions, and it's not possible to obtain, one single solution for both problems, right? If those conditions are independently specified, unless you can specify them in complementary portions of the surface. That's called a mixed BVP. In this case, I have a consistent solution, right? There's a third class. You have Dirichlet, Neumann, and mixed. So, I mean, you see that, we showed potential, an expression for the potential function, but this is not the most convenient because we have both simultaneously appearing in the expression, right? This happened because we had a particular choice of the auxiliary function psi, which was the inverse function. So if we use an adequate choice for this auxiliary function, we are going to show, we can categorize the problem into Dirichlet or Neumann. So this method is called the use of Green's function for solving the problem. And then we have also the uniqueness theorem. Okay, so it's simple, just Poisson's and also Laplace's, because Laplace is a particular case of Poisson's equations. They have either one, and the Poisson's equation has a unique solution for one of the following boundary value problems. Dirichlet, in which the potential is specified on the boundary surface, the one that surrounds the surface. Right? The other one is the Neumann. I mean, I'm showing here the type of problem, this Dirichlet boundary value problem, right? So you have a space charge, and you have a boundary. Whatever happens outside is not important. as long as you specify what is the potential on the surface. You can do whatever you want outside. If you restrict the potential to be a given function or a given constant value or a given distribution, then it doesn't matter what happened outside. That's the Dirichlet boundary value problem. The second class of problem is the Neumann, in which you specify the normal derivative relative to normal coordinates. And finally, the one that we call the mixed boundary value problem, in which we specify potential, right, on those red regions here, let's say, and the normal derivative, but in complementary regions. I mean, this is specified in this region here, which is different from that region, right? So you can do that. We're going to have also a third class of problems with the same solution. So this condition of complementary surface means that the union of the surface gives the total surface, and they do not intercept. I mean, the interception is equals to the empty set. Well, how can we show that the solution depends exclusively on one or other condition? Let's say potential or normal derivative. Well, instead of choosing the inverse function, we can choose a general class of functions called the green functions, which has a general form. I mean, they have a general form, which is inverse function plus an additional function. This is going to be called the Green's function for Poisson's equation. Well, what type of property we have for f? Well, the property is that the Laplacian of phi equals to minus 4 pi delta. It has to come out from that. So let's see what it is. So Laplacian of g is minus 4 pi delta. So what's the Laplacian of g? I mean, if I have a g, right? G of x prime equals to inverse function plus a second function. If I calculate Laplacian of g, is going to be Laplacian of this function, which is minus 4 pi delta, plus Laplacian of f, right? So what I have to do is to impose that this term is 0. So Laplacian of f has to be equals to 0. That's the property. So my green function has this property, is given by this expression, right? Provided that Laplacian of f equals 0. In other words, the f function added to the inverse function to compose the green function satisfies Laplace's equation. So you can always find green functions that have this property, right? And you can choose the property of the green function by, by tailoring the function f. Okay. So if you choose f with this g with this property, I mean the change that we are going to make in the final integral expression just showed you right there, right? Here, just to show you, I'm going to outline what are the modifications that we're going to have. Instead of this term here, we're going to have the g, right? Inverse function is replaced by g. And also here, this is the derivative of g, and this is g. So now we have a different result. What is g? Well, we have to solve for g. We have to. There's a new problem to be solved. I have to solve for the function g So that's how we end up in our formal representation of the solution. We have this solution here, right? And all we have now is to solve for G. But now, how do we solve Dirichlet boundary value problem? Well, I just make sure that I only need this information here, and this term here vanishes. For Dirichlet boundary value problem, I just specify a function GD, which is the Dirichlet Green's function, so that Laplacian of GD equals to minus 4 pi delta, right? And GD equals to 0 on the boundary. It's the same thing as solving a problem in the same geometrical construction, same boundary, where you put a point charge, because, I mean, this is in fact the potential of a point charge. It's like solving the problem of a point charge subjected to the boundary condition in which the potential, which is the solution, is 0 on the boundary. That is approximately, unless of a constant, the Green's function for the Dirichlet boundary value problem. When we do that, this term here on the surface vanishes, right? And for the GD, we have the final solution that is expressed. I mean, understand that we have to solve for GD, right? Solving for GD is like solving a problem of a point charge on a grounded, inside of a grounded surface. So I have to solve that problem, find GD. Then we have, GD is known, right? So here we have the normal derivative of G, and then your solution depends only on the, given GD, right? On the charge density and on the normal derivative of G. That's the formal solution of the Dirichlet problem, right? Well, the other thing, for Neumann, we want to use the normal derivative of the potential and not the value of the potential. So we would tend to use to set to 0 the normal derivative of G, so as to eliminate this term here, right? But that cannot be done. Let's see why. We have to be careful, because recall that the Green function satisfies this condition here. And if we integrate on the volume using Gauss's law, as we did before, we're going to have as a result that the integral over the surface of the normal derivative of G is given to, when you do the volume integral, this is minus 4 pi, it's going to be minus 4 pi. In other words, there's no way I can make it 0, the normal derivative of G. One simple choice is to make this Gn equals to minus 4 pi over the area. So if I use a constant Green function on the surface, the integral, in particular if I use this constant value, the integral is going to be satisfying this condition, right? So, cancel. So that's what we have here, right? Choose this particular. You can use that simple choice for the Neumann-Green's function. So we're going to have the normal derivative is constant, right? The 4 pi cancels. So this is nothing less than the average value, this integral over the surface divided by the surface is the average value of the potential on the boundary. So the solution has the green function for the Neumann problem. Have the density. Now we have only the normal derivative of the potential, as in the Neumann boundary value problem, after we find the solution for this problem, right? And you have an extra term, which is the average value of the potential. Your solution would be something like that. But recall that this is a constant that is not going to affect the E field, because the gradient of this constant is 0. Right? So for Neumann boundary value problem, what we do is to solve for the Neumann green function, which is a solution of a problem which is a point charge, in which the derivative is given, the normal derivative of the green function on the surface is constant. Then after we find that solution, we plug here, and we find formally the solution for the potential. Okay. So in summary, solving the problem, Poisson's equation by use of Green's function is it's formally equivalent to the solution of a problem of a general system, right? A linear system. We recall that when you have a linear system, you excite with the impulse function and have a response of the system to the impulse function. Then after you find that result, you can find the response to any excitation as a convolution of the response with that input. That's the same thing here in the problems governed by Poisson's equation. Now we're talking about problems that are in 3-dimensional or 4-dimensional space, if you have time to, but let's say 3. So we solve, the response of the system is G, the impulse response of the system, right? That's the system. System is represented by a black box governed by the Laplacian. So the impulse response is G. Then after you do that, you can find the response of the system to any driving source, which is going to be the potential. Right? Well, for the mixed boundary value problem, you can use no problem to use a function, mixed green function that has a 0 on the boundary, where the potential is given, right? And now we are not going to have that problem of finite value of derivative. You can choose a 0 derivative. You can think about it and analyze this to see if it's possible or not, but it's easy to conclude that you can also set the normal derivative to 0 in this problem here. Okay. Well, so we're going to use this to show how to solve some different problems in which you have the coexistence of electrodes and space charges. Okay, I'm going to solve some problems based on this concept of Green's function. Let's move on to the final part of the lecture. We have some interesting concepts that can be determined, some parameters that are very important in energy of electrical systems, in circuit theory, and so forth. One of these concepts is the concept of capacitance. Let's talk about linear systems in which the potential changes continuously, linearly, with the density. Suppose that you have a system with n electrodes, right? Each electrode has we energize the system, we applied potential difference between different electrodes, then we charge each one with a different charge, right? This is the nth electrode. Let's change the letter here according to my notation. This is Qn, potential is Vn. We have n electrodes. in general, we said the total, I mean, the system is neutral. What we do is to transfer charges between one electrode and the remaining electrodes. So the total charge in the system generally is zero, right? You just transfer charge from one system to the other. So we can set the nth electrode, and capital N, as being a reference electrode in which the potential is always maintained at zero. And also the charge, I mean, if I know the charge in all the other electrodes, I know the charge in this grounded electrode here, okay? Because the system is equilibrium. So it's the summation over the n minus 1 electrodes. So if you have a linear system, the charge on the remaining m minus 1 electrodes is going to be a linear function of the potential of those electrodes relative to the reference one. So, and those coefficients of proportion are called the capacitance coefficients, right? Well, those yield the degree of mutual coupling between electrodes in a system. We have a reciprocal system. I mean, you can, I'm not going to demonstrate that, but there's some implicit reciprocity system. If I charge one electrode, the amount of coupling to the other is the same as if I charge the other electrode. The same amount of charge would couple, I mean, between those two different electrodes. So we have a reciprocity property which is natural, right? Like this, Cmn equals Cnm. And also charge conservation implies that those coefficients are negative for m different than n. Let's look at that now. And let's try to understand in a more intuitive way, okay? Let's look at the system of 3 electrodes, okay? What is exactly those coefficients? Let's assume that we have a system of 3 conductors, right? Like shown here. Conductor 1, conductor 2, conductor 3, right? Then I energize the system such that I apply a voltage on this electrode here, and I ground the second electrode, and this is the reference one, okay? What happens? I mean, notice that if you use Gauss's law, right? If I use a Gaussian surface on this first electrode, it means that you have Q coulombs going out of this electrode here. And these Q coulombs, I can calculate also the flux around on a surface that encloses this electrode here. Because not all of the lines that go out from this electrode end up on this one. We have an induced charge, and also you see that the lines, they end on the electrode Q2 partly. So I have induced negative charge, and the magnitude of the charge is smaller than Q, because not all of the lines, right, goes to the second electrode. In addition, I mean, part of the lines go to this ground electrode. I can make a Gaussian surface here and calculate the amount of charge that is induced, you know, on the surface. So it's clear from the construction that the amount of charge on either electrode is going to be smaller in magnitude than the total charge Q, just by Gauss's law, right? So as the lines terminate on this grounded electrodes, okay, notice that I cannot have any line that comes, for instance, I cannot make any construct like this, a line that comes here to end here, right? Because this is at zero potential, this is at zero potential. If that were true, the line integral between these 2 points would be not zero, right? But they are grounded, so the line integral of E field here equals to 0. So there's no way I can have a line that goes like this. I would have an integral that's non-zero. So there's no way I have a line coming from a grounded electrode and ending in the other grounded electrode. There's no way I can do that. I mean, all the lines have to come out from the positively charged electrode, which is this one here, and end in the others and the other grounded electrodes. And also, I mean, the amount of charge on the Q2 and Q3, either one, are smaller, right? They are negative and they are smaller in magnitude. So there's no positive charge in the grounded electrodes. So, I mean, in other words, I mean, you have magnitude of Q2 is smaller than Q, magnitude of Q3 is smaller than Q, and both charges are negative, so the product is positive. Okay, so what happened? Let's see how. I mean, recall that in this, in our definition, I don't have to consider this electrode here, right? I mean, this one here. This is the third, n equals 3, capital N equals 3. This is the reference electrode. So I'm going to make the relation in those two here. Okay? So the charge in the second electrode equals to the coupling coefficient C21 times the potential on the first one plus C22 times V2. But if I set V2 equals 0, okay, and V1 equals to V, so we have C21 is the charge on electrode 2 divided by the potential of electrode 1, which is positive by definition. So this quantity is indeed negative. So the capacitance coefficient is negative. I mean, the coupling coefficient for different. It means that, I mean, it means the coupling coefficient means the amount of flux that comes from that electrode 1 to electrode 2 for a given energization. Okay, that's the amount of charge with sign. Okay. You can eliminate the sign, I mean, but just notice that this is the sign that's induced in the second electrode. This is the same to say as that is the amount of coupled field lines that come from electrode 1 that couple directly to electrode 2. So you get that portion is going to be the amount of coulombs that is coupled between those two elements. It's easy to understand why this is reciprocal, because I would have the same behavior. I could change the energization, and the field lines would be the same. Would have the same behavior, you know. So the C21, C12 are the same. Okay, so that's how we proved that. For instance, let's look at two electrodes. So when I have two electrodes, one of them is the reference. Let's say electrode 2 is the reference electrode, right? So I don't have to worry about C12. There's no mutual coupling here because we're talking about only a reference electrode and the other one, the capacitor, simple capacitor. So we only have a coefficient which is C11 equals C. So the charge on electrode 1 equals C11 V1 because the second one is grounded. That's called CV. So the capacitance is the charge on the positive electrode, which is a positive number, right? Divided by the potential drop between the two electrodes. I'll let you give it to you some examples. I mean, I'll give it to you for you to calculate some of the capacitance as boundary value problems. Here, to calculate the capacitance of a system, I'm going to outline the procedure here. I'm going to leave for you to calculate those capacitances that I have in my class notes. So in general, I have for two electrodes, what do you do, right? The formal methods for, let's say, talk about two electrodes, is to energize the system. We have capacitance doesn't depend on the potential difference. Doesn't depend on the amounts of charge because the system is linear. Capacitance is charge transferred by potential difference. As the system is linear, this only depends on permittivity, right? And geometrical dimensions. That's what capacitance depends on. Okay? So, how do you do the problem? We assume that one potential, one electrode is at a given potential, the other one is grounded. So have a region that is these two electrodes are in a medium that is infinite in region. We have to solve for the potential function, subject to the boundary condition. How to solve it? Well, we have to solve Laplacian of phi equals 0. Let's say sigma 1, sigma 2. Let's say that phi of sigma 1 equals v. There's a BVP, right? Phi of sigma 2 equals 0. So you find this function, then you determine E equals minus gradient of phi. The first part is solving Laplace equation. Second is solving for the field. Third is determining D equals epsilon E. And finally, we go on the surface. You calculate the surface charge density, which is normal D, okay? And after that, you calculate the charge on the positive electrodes, which is simply minus epsilon integral of on the positive electrode of the normal derivative of the potential. So we have the charge. Formally, that's how you calculate capacitance. Once you have that, this is going to be proportional to V, and you determine Q over V, which is going to be the capacitance. That's how we do it. That's the formal method of solving for the capacitance. I'm just doing this quickly because this is a theme for the undergraduate course. I'm just doing quickly, just outlining how it is. Solve a boundary value problem, find the potential, find E field, find D, find surface density of charge on the positive electrode, calculate the total charge divided by V, then you have the capacitance. Okay, this is very, if you have more conductors, it's going to be more complicated because the boundary value problem is more complex. Okay, so you can do that procedure to solve for some, some structures. This is an approximation, assuming that, let's say this is one of the dimensions. There's another dimension normal to the plane of the capacitor here. Let's say that we have a width here, right? So for D much smaller than W, you can assume that the potential doesn't depend on this coordinate, on the normal coordinate, but depends only on this one. Then you have a potential Cartesian coordinates that depends linearly on the coordinate. You can easily find the field, the induced charge on this electrode. Let's apply a voltage V0 here. Then you find that the capacitance is approximately epsilon area over D. Okay, so this is recall, right? Farads per meters. This is meter, so capacitance is in farad. Okay, so capacitance is unity of permittivity times area over length. In general, you can estimate the capacitance looking at the ratio between the area of your system and the separation of electrodes typically. So it's going to increase linearly with dimension, with the linear dimension. Capacitance increases linearly with dimension. If you have a capacitor, you make everything proportional, increase each length proportionally, your capacitance is going to increase linearly with this scale factor. This is an important concept, okay? Then you can do other situations. You can calculate the capacitance of an isolated sphere, electrodes, of radius A, simply that formula, which shows that the capacitance increases linearly with the radius of the sphere, something I mentioned in one of those lectures before, right? We have a spherical capacitor. We have two concentric spherical shells. You can show that the capacitance is very closely similar to that of the planar capacitor, but we have here an effective area, which is the area of a sphere have an intermediate radius, a bar, which is the geometrical means between A and B. So it's like this. You have the result is that the capacitance of spherical capacitor is the epsilon effective area over separation D, which is B minus A, right? This is the area of the spherical imaginary surface, intermediate surface. Okay, just the energy of a set of conductors can be calculated, right? Using those capacitance coefficients, right? It's very easy to determine. Have a set of conductors. You can use those concepts I just showed before to determine the energy. This is a linear system. In the point of view of the field source, it's given by this expression here. And because the charges are concentrated on surfaces, this integral is going to break, can break it up in a sum of surface integrals involving the potential in each surface, which is constant, right? And the result is the integral on each surface of the density function, which gives the total charge. So the energy is very easy when you have a set of electrodes. Is 1/2 of products like those. Okay, recall that the nth electrode is grounded, so I can use this condition here. The charge in the nth electrode is the system is electrically neutral, for instance. I can use our relationship between charge and capacitance to show that the energy for several electrodes will be calculated with basis on this expression, right? Easy to show, so leave you to work this out to demonstrate this. So if you have two electrodes, you have a capacitor, single capacitor, simple. So I ground one of them, right? So the energy is 1/2 of Q of the positive electrode times the potential of that electrode relative to the grounded one. So in terms of capacitance, you can write like this or like that. So you fix the potential, you have that. Fix the charge, you have that. Okay? Now, final part of this class, we want to, before going to solving more complicated problems in which the potential depends on more than one variable, we want to establish a very simple principle that allows you to determine forces in internal parts of systems, be either electrical, magnetic, mechanical, and so forth. For any physical system, you have internal forces. Okay. If, for instance, you have a configuration of charges, two charges, either positive or different signs, we imagine that they are being held at this position, right, where they are. If we just let the system go, the system is going to either be, the charge will be either attracted or repelled, depending on the signs. But the tendency of the system is always to move to a new energy state which is smaller than the previous one. So any system tends to be configured so that the energy is minimum, right? The smallest value possible. So when you have two charges, let's say two positive charges, they want to repel, they want to move away from each other. We imagine an external agent holding those charges together. So the agent is applying a force against the natural internal force of the system. So the agent, if he moved one of the charges relative to the other, he would increase the energy, right? So the external agent applies a force that would increase the energy. Internal force have strengths that try to reduce the energy, okay? So if we imagine that the system wants to change to a lower state of energy, the external agent would apply a force that would produce work. Fx is the external agent, force applied by the agent, which would increase the energy. You notice that differential of a function of three variables, let's say in 3D space, if we are talking about displacement of coordinates, of some coordinates in the system, so then we have that displacement dot gradient of u gives the differential change in energy. So as I mentioned, the external agent applies a force that's against the internal system force, let's call it minus F. So if we equate those things, we have, F internal is F dot dl equals minus dl gradient of u. Of course, these two things are equal because these are independent on the direction of dl, okay? So there's only one possibility, F equals to minus gradient of u, of the energy of the system. So the internal force is that which is related to the energy by minus gradient of u. So that's the criterion we have to determine forces in parts of a system, okay? So this is the principle of virtual work. We imagine that the system itself makes a small displacement of the configuration. This displacement is represented by this differential displacement. Imagine the external agent would apply a force against that, so the force of the agent would increase the energy. So we have that relation. Okay. So let's do two examples. I could do this example calculating the capacitance of the system and calculate the change using that formula I just showed you. But I'm going to calculate using the field point of view, using several concepts. Let's assume that we have a parallel plate capacitor, okay, like this one. Let's assume that to the plane, inside, you have the x direction is to the right, z direction to the top, and entering the plane of the capacitor, the plane of you're seeing there, you have a unit length 1. So you can have the area of this capacitor is L times 1, right? So in this problem, if you solve the boundary value problem, potential is a linear function of coordinate z. So field is v over d. It's easy to show that, to determine that. And also, suppose that you are entering with, let me make a better drawing here. We have 2 electrodes, right? I'm going to make a very quick drawing here. Then we are entering with a dielectric material into this. We are trying to put, we are trying to see if this dielectric is pulled inside. If I put in some position x, if this dielectric is going to be pulled to the inner of the capacitor, or is going to be repelled by it, right? What's the natural tendency of the system? You know that natural tendency is to the energy to be reduced. So what we have to do is to calculate the energy. So if you solve this problem, we see that because E tangential is continuous, let's assume that we have the dielectric relative permittivity epsilon r entered, is placed at a position x. We're going to change x by a small amount to see how the energy is going to change. So we're going to find the force, internal force. So the E field here, we assume that the potential is fixed, okay? That's the first example, fixed potential. So the E field is uniform, and also the tangential field is continuous, so the field has to be the same on both regions, okay? And because the potential is fixed, this E field is always constant, independent on the position of the dielectric in the capacitor. Okay? So the energy can be calculated using the point of view, just remembering 1/2 of epsilon. The original formula for a linear system is epsilon, volume integral of d dot E dV, right? The energy density in the dielectric is 1/2 of epsilon E square. Let's call let's say in the dielectric UD, and in the vacuum is, which is the integrand here, is 1/2 of epsilon 0 E square. Right? So you see that there's more energy in the dielectric than in the vacuum, right? If we put more, we already know the answer. If we put more dielectric, the energy is going to be larger. The amount of energy is going to increase because you're going to have more dielectric, and E is always constant. So I just anticipate to you that the tendency is the system to repel the penetration of the dielectric. So let's see how it is. Let's show that. So calculating the energy, I'll leave for you to calculate. This is the volume integral already, right? Factor of 2 here. Relative permittivity, I put epsilon 0 here. So I have the square of field. Then X is the length of the dielectric. H is the height, which is the volume. And times 1, I didn't put here because it's the depth to the plane of the page. And the remaining part of the energy is this one here, which is on the vacuum part, right? So you can combine those things and determine the energy as a function of x. So that's the energy stored in the system. Let's calculate the gradient. Let's say we're talking about the displacement on the x direction. So it's going to be, let's calculate du dx, right? The plus the gradient. And du dx is positive, so it means that the force is minus du dx. The force is given by minus gradient. The force is given by this expression here. So this internal force on the dielectric is negative, right? So the dielectric tends to move away. If you try to put the dielectric on pair of electrodes that are at a fixed potential difference, the field is going to repel the entrance of the dielectric. Okay? So that's one result. The other problem is dielectric entering an isolated capacitor. Now the situation is different. Now the charge is constant, given by Q. Okay? And as you move the dielectric inside, as we imagine a virtual displacement of the dielectric inside of the capacitor, the part of the charge is going to be Qx, and part of the charge will be on the other side. We can imagine that, again, for a given configuration, this thing is uniformly distributed. Okay? Then we have the field. Again, the field is the same on both sides, but now the field depends on how deep the dielectric enters the system. We're going to calculate that. Remember, E field is the tangential component is continuous, right? So we can calculate the flux density, which is charge per unit area. Area is equals to, on the dielectric, x times 1, which is 1 is the depth of the capacitor. So the field on first dielectric is d over epsilon. This is, in fact, rigorously, you have an epsilon 0 here, right? But I'm omitting that to avoid it. Just forget the epsilon 0. On the other hand, the flux density on the vacuum is going to be the charge over the area, which is now L minus X, right? Divide L minus X times 1, which is the width along the y direction. But because E2 equals E1, you have the field also on the vacuum is the same. Qx is the same. Those are the same. The D changes, but not E, right? So you can calculate with those, can calculate the energy again, okay, by the same formula. Volume integral of epsilon E square, right? I leave for you to calculate this. That's the ratio that appears here, the Qx over x square, is given by this function here. And then you can calculate, those factors are present here, right? We have an L minus X there. So you can calculate the energy now. It's going to be a function that has an inverse function here. And again, can calculate the internal force. Now the force is going to be positive. Right? The internal force. The natural force of the system. For a virtual displacement, the force would be favorable to the entrance of the dielectric. So the dielectric will be pulled, towards, to enter, would be attracted to the inner part of the capacitor. So that's the result, right? So this is important. If you have a magnet, right, and have a bar, you can determine, what is going to be the trend, if the bar is going to be repelled or attracted, and you can even calculate the force by using this principle. This is a general principle for different configurations that can be employed. So that's what we have. The force is a nonlinear function, right? It keeps decreasing. So what happens here is that we have polarization charges that are induced, right? And the charge come here I mean, the charge try to pull those polarization charges. You know, I mean, in fact, it's the other way. It's minus and plus. So we have attraction between the charges. It tries to pull the dielectric to the inner part of the capacitor. Okay, so that's what we have for today. It was a lot of information, but basically those are basic concepts on how to solve Poisson's equation and what are the energy concepts that are relevant for electrostatics. I see you next time. Till then, bye-bye.